All right, moving into more of the practical side of thermal imaging rather than just the theoretical, we're going to be looking at the thermal properties of objects and how we kind of assess that. So there's a few indicators that allow us to adjust for the thermal, or like to be able to interpret the thermal images. The first thing is understanding those basic physical processes that control the interaction between thermal energy and matter. So, as you know, water tends to hold heat for much longer. Rocks will cool off rather quickly. Metal cools really fast. It doesn't even hold heat hardly at all, which means it has a really low emissivity. And so there's this like really important interaction between those two concepts. And so you have to understand that if you're planning on going into thermography, you have to know your materials really well. So when we're looking at over time, for example, and how certain aspects are impacted by, like the materials are impacted by the time of day or the the time of day, the amount of sunlight, the amount of energy that it's receiving. We can take a look at this little diagram here. So to be able to do a measurement, we have to really be aware of what time of day we are going. So we can see in this case at night, we have a separation between the water line and the dry soils and rock line. And so it's very stable all the way through the night. You can see that it kind of goes stable here as well. That stability allows us to really examine the thermal properties of materials in a bit greater detail, just because we know that all the way through the night it's just going to stay the same. But as the sun comes up, it's going to start heating up the land, and we're going to start seeing the land really, really getting warm. And water also starts to increase in temperature as the day goes on, but not as much. So by about noon or a little bit after noon, we have a really big difference between soils and rocks and water. So if we're looking for that contrast, then we know that midday is what we're going for. The one point that you don't want to go out and do thermal imaging is at these crossover points. So the reason we don't want to go during those crossover points is because everything looks the same. There's no identification between the two types of materials between land and water, and so therefore it just becomes a gray image. So you do want to make sure that you're getting some sort of contrast, whether it be at night when it's stable or during the day when you're looking at this high contrast, but never at these crossover points. So diurnally, every day you have to be aware of those times. A lot of airborne imaging actually happens at night, around midnight or really early in the morning before the sun comes up. And that's just merely because the stability is actually a better time to do it. So once we've got that, now we can get into the actual interpretation of these images. So as I mentioned, you can do thermal imaging day or night, and we can acquire our images based on like the different heating patterns we can examine that happen at night rather than during the day. So like we were talking about it midday, we have all kinds of crazy things happening. Like you can go out onto black pavement in the middle of summer. It's gonna be super, super hot, and then you step on concrete and it's like it's not as hot, it's kind of actually cool. And then you step in grass and it's really cool. So that super high contrast it actually like almost overwhelms the system. If we do it at night, we can remove that overwhelming, and then we're not actually too worried as well about what exact time of day we're at, because if we happen to get out a little bit later, like something held us up and it's now we're going to head out for 1 o'clock in the morning and now we're heading out at 2:30, that difference doesn't make any, like that time difference doesn't impact my images. But if I come out in the middle of the day, that hour and a half can have a huge impact on how I interpret my images. So like I say here, pre-dawn images are preferred, so middle of the night. And we do need to consider fog, dew, and frost because all of those have water in them. And water will cause a reduction in the thermal energy actually being emitted because it'll get trapped within it because water has a very high emissivity and it absorbs very, very quickly. So fog tends to make it almost opaque. Dew will make it almost opaque. Frost will also make it kind of opaque. Like we won't see that heat. So if you do get something in daytime, make sure you go out mid-afternoon. That's when the highest peak is. And that's when our radiant temperatures are at a maximum. So it does kind of give us a little bit more information based on that maximum if you're concerned about it for whatever your application is. Because actually, an example of that would be if you're releasing wastewater into cleaned wastewater into a river. You may want to see if that wastewater is actually increasing the temperature during the daytime as well as at night. So, and then you can see that mixture between the two and when does it actually cool off once it gets further down from a factory. So I've already described that one. So here's an example of daytime and nighttime images. So you can see here we've got this area during the day compared to at night. You get a very different perspective of what this image looks like. And over here, we have something going on around this loop, and you can see that here even more so. So whatever these little pockets are, they might be just little ponds, which is possible because it's warmer at night than it is during the day. And so that's a possibility as well. But you can also see over here that we have little round objects that show up and they're warm at night and they're showing up dark over here. So again, and they might be pools or something that people have. And just again, you can see that interpretation becomes really like a challenge. But you can really see the difference between what happens during the day and what happens during the night. The interpretation is different. And there, of course, has to be an application for you to go out for whichever is going to work best. You can see, for example, these houses, they're all black at night, and here they're all white. So that's the rooftop material that is having an impact there. So brighter tones tend to be warmer at radiant temperatures. Darker tones show the cooler radiant temperatures. We need to know the time of day, like I mentioned many times over and over again, because it's really super important. So the other thing is what can we really identify in our thermal images? The first one is water versus soil and rock. So water is always cooler in the day, and then it's warmer at night. So it's an easy identification. Vegetation itself, trees are cooler during the day and then warmer at night. And yes, they are, even though you might feel the leaves and you're like, it doesn't make a difference. But yes, that's true. They appear anyways, cooler during the day and warmer at night. Grass and other low-lying vegetation is warm during the day, and then it approaches local air temperature after that. And then damp ground is cool all the time. So you always see the cool. It always appears really dark. So we have consolidated, which is like dense, and unconsolidated, which is loose materials. It depends on the thermal inertia of the material, and so the contrast tones are going to be affected by that. So if you have two that are right beside each other, sometimes they will show a difference in contrast, sometimes they won't. But generally rocks, which are like consolidated soil, they appear cooler than unconsolidated materials during the day, and then it will reverse at night. Pavement is warm all the time, and then metal surfaces are always dark. And you could tell that if you heated up your hands and you put your hands on a metal bar and then you let go of it and then you touched it again just a few seconds later, it's going to already start to feel cool. So metal surfaces just don't radiate heat very well. And then there's always high temperature sources, so forest fires, geothermal sources, active volcanoes. Those ones don't matter what time of day they are. An active volcano doesn't wait till it hits 9 a.m. before it does its thing. So, and they're just pretty much fairly constant because they're usually high temperature sources. So I just realized my next slide is going to be double, so I'm going to change that. So there's covered features that also have an impact on my imaging. So buried heating lines, streams underneath the vegetation canopy, I can see those. You can actually see roots of trees as well underneath like a thin soil layer. You'll identify them as well, which is kind of a neat thing in like a cold soil. Surface winds is another thing, of course. The surface winds also cause a lot of problems. They kind of push around the thermal energy, and because they move it, it causes satellite images a lot of interesting, fun things that they have to correct for. So the faster the wind, the lower the contrast. But you do end up with like weird streaks and stuff happening, which is actually really fascinating when you see it in there. You're like, oh, look at that. You can also get shadows from winds if it's really high. So it's kind of a neat thing with thermal energy. And then, of course, anything that has to do with water, it causes cooler and more uniform temperatures because it just kind of neutralizes everything. And then clouds and fog just kind of like mask everything. You can't see through clouds and fog. So if you do end up with some if you do end up with some energy, it's generally very distorted where it's actually located because it has been dissipating through that and like absorbed and re-emitted from all the water molecules in the atmosphere. The last one is ghosts. Ooh. So what this is, a ghost is, a thermal ghost, is if you were to put your hand on a table and then you moved it and you like took an image of the table, you're going to still see where your hand was. And that's considered a ghost. And ghost hunters, if you've ever watched that video, this is exactly what they do, right? So they will have somebody sit in a seat for a little bit and heat it up. And then they'll bring in their cameras and that person gets up and moves. And they'll put like an insulated floor down for that person to remove themselves. And then they pull the floor out and then they come in with their camera and they will see this like imprint on the chair. Footprints across the floor, you just send a dog across the floor and you've got dog footprints and they last there for quite a while because of just the nature of how thermal ghosts work. So this is also why you can't hide from run on foot and hide from a cop. You know, if you have a helicopter chasing you and they're using thermal imaging at night, they're going to see your footprints and they can follow that. They also can, if you are using an escape car, they're going to see which one is hotter because the energy within the engine shows, and then they're also going to see you. They can also see the handprint on the door for a little bit longer because everything's now fiberglass, not metal, and it's painted too. So yeah, there's a lot of fun stuff with thermal imaging, especially when it comes to ghosts. You can't hide from anything anymore. So the next things that we can also interpret from that is dust and smoke. So those actually you can see right through. You'll see ashes, like so forest fires. You can track like hot ash in the air, but the smoke doesn't actually impact it. High humidity areas tend to appear cooler and they have more uniform temperatures. Again, it's just because there's more water that's in there. And then there's also temperature inversions. So if you have a hill, it's going to be hot up top and cool at the bottom. And then during the daytime, if you have a canyon, it's hot at the bottom, cool at the top. So these temperature inversions happen all the time in those. So you have to keep in mind that we do have an error, like a terrain displacement error, just because of the fact that hills and valleys work like that. The best time to do thermal images is through clear skies with no surface wind and low humidity. And then we've talked about the best time of day. So daytime are great for differential solar heating and looking at shadows of topographic features. Anything else that requires any true analytical, maybe not true, I can't say that. because the other stuff is also true. It's all true. But like geological and physical interpretations, they require nighttime images. So if you're doing houses, like you're doing thermography of a house, you want to do it at night because then all that solar differential information has been reduced. And then last but not least, the surface moisture and dense vegetation. So if you have a lot of surface moisture, like dew on your vegetation or lasting raindrops on the vegetation, it's going to mask everything. You're not going to see it that much. So really, thermal images are best in arid or semi-arid environments. Like Calgary is a really good example. Maybe not this summer since it like stormed every day, but normally it's a pretty dry area, so they work really well in those environments. So that kind of wraps up my interpretations side of things. And in the lab, we're going to be looking at some airborne images, and you're going to do some interpretation on your own. And of course, I'm not looking for expert interpretation because that's like a whole career in itself. But if stuff like this really interests you, I have had several students go and work in the forest firefighting industry doing thermal imaging, and they've really enjoyed it. They've loved doing that. You fly out at 2 o'clock in the morning, you're imaging these fires, you're coming back, you're creating the maps, and then you're sending it off to the client like before they even go out to the field, right? So it's really fascinating stuff. You can also do thermography on the ground where you're looking at helping people fix their homes so that they can be more energy efficient. And so it's another career option as well. So there's lots of career options in this, and you can go take a certificate in thermography and start up your own business if you wanted to. So last but not least of like the physics. I need to throw this in here because these three terms I've kind of mentioned throughout, and I just need to make sure that you know the difference between them. So there are not types, but measures, I guess, of thermal energy. One of them is conductivity, and that is the rate at which the heat passes through a material. In remote sensing, it is very hard for us to measure that from a distance. That's kind of something that's been determined before. So, for example, if you have a snowpack on top of ice, the snowpack acts as an insulator for thermal energy, and therefore the ocean is warm and you have an insulated blanket up top, it actually reduces the thickness of the ice, which is kind of a crazy thought, right? They're like, oh, I thought that snow would actually maintain the ice, but as the oceans are warming, we're going to have a warmer ocean. We have a blanket sitting on top of the ice, and so the ice is actually melting from the bottom. Then we have thermal capacity, and that is a measure of how well a material stores the heat. So looking at water, the oceans really help with keeping our Earth warm, and it circulates the heat throughout it very, very effectively. So if we look at how much energy it actually stores, like water has extremely high thermal capacity because it can hold so much of that energy. Then we've got the atmosphere, which also has a little bit of a thermal capacity, but nowhere near the capacity of the water. So as we end up increasing the amount of heat in our water, we end up, because of the global warming, the water heat increases, and therefore it stores more heat. Then the atmosphere also heats up and also stores a little bit of heat. So between the two of them, that if you increase one, you're going to end up with a positive feedback loop with the other one. So I heat up my atmosphere, I'm going to heat up my water. My water heats up, it's going to heat up the air. The air heats up, it heats up the water, and you just can't get out of this cycle. So it's an interesting concept, but it is the truth. Then the last one is thermal inertia, and that is how well a material responds to temperature changes. So this is, I increase my temperature, what does it do? And does it actually represent that temperature change? Does it do anything different? So for example, water, as you heat it, it expands. So if we think about our oceans, they talk about the oceans rising. One of the measures that is rarely put into place is the thermal inertia about how the water expands as it increases in temperature. When you start adding in that math, the numbers look much, much worse. So that's another thing about thermodynamics. So this is all stuff that we see. It's all physics based, and I'm using examples with oceans and ice because that was my background. And that really kind of wraps up my thermal remote sensing theory. Check out these different references that I've got. They've got some interesting stuff on them. And that will be it, and we'll be moving on to microwaves next week.